In the previous lecture, I gave an introduction to gravitational waves. At the time I recorded that lecture, my plan for this lecture was to begin discussing some of the mathematical details of gravitational waves. In particular, I had planned to cover the linearized Einstein equations and gauge conditions, but I've changed my mind. I'll cover those topics later. For now, I think it makes more sense to discuss some of the details of interferometer gravitational wave detectors. One of the topics I want to cover is a common confusion about using light to detect gravitational waves. The confusion can be expressed in the following way. Since a gravitational wave causes space to expand and contract, it also expands and contracts light waves. In other words, it causes light to be redshifted and blueshifted. So if this is the case, then how can light be used to measure gravitational waves? I'll explain this misconception in more detail in a minute. For now, let me back up and summarize the main results from the last lecture. In that lecture, I gave an example of a gravitational wave. The metric for this wave has the form g mu nu equals eta mu nu plus h mu nu, where eta mu nu is the flat space Minkowski metric, and h is a small perturbation. The coordinates for this metric are t, x, y, and z, and the perturbation h is a diagonal matrix with entries 0, a times sine of omega t minus z, minus a times sine of omega t minus z, and 0. Now this perturbation is small, so this dimensionless amplitude a must be small, much less than 1. Now you can check that this metric satisfies the vacuum Einstein equations. To linear order in the small parameter a. So in other words, capital G mu nu is equal to 0 plus corrections of order a squared. These corrections are telling us that this metric, eta plus h, is an approximation to an exact gravitational wave solution. For the exact solution, the metric would have higher order terms in the parameter a, but in practice the parameter a is very small, on the order of 10 to the minus 21. So this approximation, where we drop the higher order terms in a in the metric, is really quite good. And by the way, this gravitational wave example with this metric perturbation h, this is a plain monochromatic wave propagating in the z direction. With what is referred to as plus polarization. Now in the last lecture we examined the geodesic equations. So let's let x mu of tau denote a time-like world line, where tau is proper time along the world line. And of course the space-time coordinates, the x mu's, are t, x, y, and z. So this is t of tau, x of tau, y of tau, and z of tau. Now what we found in the last lecture was a family of geodesics given by t of tau equals tau, x of tau equals a constant, x naught, y of tau equals a constant, y naught, and z of tau equals z naught. In other words, there's a family of freely falling, unaccelerated particles Of course, freely falling implies that they're unaccelerated, and vice versa, that remain at rest in this coordinate system. In other words, they remain at constant values of the spatial coordinates, the x, y, and z coordinates. As an example, we can consider a ring of test masses in the z=0 plane. So here's the y-axis, and this is the x-axis, and this is the ring of test masses. Recall that our gravitational wave is propagating in the z direction. As it passes through this region, the ring of particles stay in place in these coordinates. So they stay in place. We also examined the geodesics using Fermi normal coordinates. We called them t bar, x bar, y bar, and z bar. These coordinates are tied to the local inertial frame defined by an observer who sits at the origin. In particular, t bar is proper time for the observer, and the spatial coordinates, x bar, y bar, z bar, are Cartesian coordinates for the space-like slices. In other words, x bar, y bar, and z bar span the set of events that the observer sees as simultaneous. We can now draw this same ring of particles in Fermi normal coordinates. So here's the y bar axis, and this is the x bar axis. Initially, at time t bar equals 0, the ring of particles looks like a circle. But as the gravitational wave passes, it first causes the ring to elongate in the x direction and shorten in the y direction. So this is the shape of the ring after 1/4 of a gravitational wave period. At 1/2 period, the ring has its original shape. Then after 3/4 period, the ring is elongated in the y direction and shortened in the x direction. So this is the shape of the ring at 3/4 period. Three-fourths of a gravitational wave period. Of course, after a full period, the ring has its original shape again. Now, both of these pictures are correct, but it's this picture that uses Fermi normal coordinates that shows what an observer would actually see as the gravitational wave passes by. And by the way, the original coordinate system used to draw this picture, the t, x, y, z coordinates, are referred to as transverse traceless coordinates. T, x, y, and z, sometimes abbreviated TT. So this is the picture of the effect of the gravitational wave on a ring of test particles in the TT coordinate system. And this is the picture in the Fermi normal coordinate system. The obvious advantage of the Fermi normal coordinate system is that it shows us very clearly the physical effects of the gravitational wave. But the advantage of the TT coordinates is that the metric in these coordinates has an especially simple form. Now, in discussing the physical effects of a gravitational wave, I want to be careful about the wording I use. Notice that I don't say that the gravitational wave is pushing and pulling on these test masses, even though sometimes it's tempting to use that Newtonian language. Remember, each particle in this ring follows a geodesic, an unaccelerated world line. So if you were riding along one of these particles, you wouldn't experience any sense of motion or acceleration. So the relative motion between these particles is caused by an expansion and contraction of space by the gravitational wave. So the relative motion is caused by expansion and contraction of space. And note that for our example gravitational wave that's traveling in the z direction, this expansion and contraction is homogeneous in the x and y directions. In other words, d by dx and d by dy are Killing vector fields. So this tells us that we have translational symmetries in the x and y directions. So we can consider a lattice of test masses, freely falling particles, in the z equals 0 plane. A passing gravitational wave will first cause space to expand in the x direction. So all of these distances increase. And at the same time, space contracts in the y direction, causing all of these distances to decrease. And of course, half a period later, the gravitational wave causes a contraction of space in the x direction and an expansion of space in the y direction. So how does an interferometer gravitational wave detector work? The basic idea uses 3 test masses. So let's assume those test masses are in the z equals 0 plane. So here's the y-axis, and this is the x-axis. One test mass sits at the origin, and the other 2 test masses are on the x and y axes. In the ground-based interferometers, this test mass is at the corner station, and these test masses are at the end stations. Laser light is produced at the corner station and the beam is split. Half the light travels down the X arm and it reflects off of a mirror attached to the test mass, then returns to the corner station. The other half of the light travels along the Y arm, reflects off of a mirror, and returns to the corner station. The 2 light waves are recombined at the corner station. If the arms have the same length, so the waves travel the same distance, then the waves will be in phase when they're recombined. On the other hand, if one arm is a bit longer than the other, there will be a relative phase shift between the 2 waves. and this will show up as an interference pattern when the waves are recombined. So as we know, a gravitational wave traveling in, say, the z direction will cause space to expand and contract in the x and y directions. First, this length along the x-arm will be expanded while this length along the y-arm contracts. Then half a period later, it's the other way around. This arm contracts and this arm expands. And those changes in the arm lengths then are detected in the interference pattern in the light waves when they're recombined at the corner station. So this is the basic idea behind the ground-based gravitational wave detectors, such as LIGO, Virgo, Kagra, Indigo. And it's also the basic idea behind the space-based LISA mission, with the main difference being that the end stations and corner stations are replaced by satellites. Now, one of the issues you might have with this explanation is that the test masses, at least for the ground-based gravitational wave detectors, the test masses are not freely falling. They're not moving along geodesics. The test masses are actually suspended from the ceiling of the end stations or the corner station. Let me draw a picture of one of these test masses, say this test mass that's on the x-axis. So here's the test mass, and this is a side view. So the x-axis is in this direction and the z-axis points upward. And the test mass is suspended from the ceiling with a thin wire. So this is the wire. And this is the ceiling. And here's the laser light traveling down the x-arm and reflecting off the test mass. So the test mass is accelerating upward in this picture, upward in the z direction due to the tension in the wire, but it can swing back and forth in the x direction. And if you consider the time scale of the gravitational waves coming from a binary black hole or neutron star collision, so a binary black hole and neutron star collision will produce waves of frequency around 100 hertz, which is a time period of about 1/100th of a second. So on this time scale, this mass is essentially free to move in the x direction. In fact, on such a short time scale, we can think of the test mass as being unaccelerated even in the z direction. Imagine just as the gravitational wave hits that we cut the wire that suspends the test mass. Then the test mass will be truly in free fall. It will be truly unaccelerated. So, of course, the mass will fall to the floor, but for a few hundredths of a second, it will hardly move at all. This shows that over the time scale of a detection, we can think of the test mass as following a geodesic. Now let's take a closer look at how the light travels along the arms of the interferometer as the arm lengths change due to the passing gravitational wave. So here again is a sketch. This is the y-axis of the interferometer, the x-axis. These are the test masses at the corner station and end stations. And remember, light is produced at the corner station and it's split so that half goes down the x-axis, is reflected and comes back. The other half goes down the y-axis, is reflected back. The light is then recombined to form an interference pattern that encodes any changes in the lengths of the arms relative to one another. Let's recall that the metric for our example gravitational wave is a diagonal matrix. G mu nu has entries -1, 1 plus a times sine of omega t minus z, 1 minus a times sine of omega t minus z, and 1. Now let's see if we can give a rough estimate of the phase difference between the light that travels down the X and Y arms. Let's first compute the length of the X arm at some time t0. So for the X arm at time t sub 0, and we'll take z equals 0. So we're assuming that the interferometer lies in the z equals 0 plane. Then from the line element, we have ds squared equals 1 plus a times sine of omega t minus z, but t is t0 and z is 0. All of that times dx squared. We'll also assume that this test mass sits at a coordinate location x equals L. Remember, in the TT coordinates, the transverse traceless coordinates, the free particles, the freely falling particles, remain at a constant coordinate location as the gravitational wave passes by. So we'll let that constant be capital L. And now, taking the square root of the line element, we have ds equals square root of 1 plus a sine of omega t0 times dx. And then integrating, we find the proper length of the X arm, let's call that the X length, equals 1 plus a sine of omega t0 to the 1/2 power times the integral of dx is L. And now let's remember that a is a small parameter, and we're carrying out all of our calculations to linear order in a. So this is 1 plus a over 2 times sine of omega t0 times L. And likewise, if we compute the y length, the proper length of the y arm at time t0, we find 1 minus a over 2 times sine of omega t0 times L. Now let's compute the time it takes light to travel the length of the X arm and back. So that's the round trip travel time, light travel time. For the X arm, let's call it t round trip comma x. That's just equal to 2 times this proper length, the x length, divided by the speed of light, c. So that's equal to 2L over c times 1 plus a over 2 times sine of omega t0. And similarly, the round trip travel time for light moving down and back the y arm is 2 times the y length over c, which is 2L over c times 1 minus a over 2 times sine of omega t0. Now the time difference between these two results let's call it delta t, is equal to 2L over c times a sine of omega t0. And now the phase difference between the two light waves, let's call it delta phi, is equal to the angular frequency of the light, omega sub light, times the time difference. So putting this all together, we find the phase difference, delta phi, is equal to 2LA times the light angular frequency divided by the speed of light times sine of omega t0. And it's important to notice, of course, that the omega here that multiplies the t0 is the angular frequency of the gravitational wave, whereas this is the angular frequency of the light wave. Now, in deriving this result, I've made a few approximations. The first approximation is that the arm lengths are constant during the light travel time. This is really not a bad approximation. If you consider the light travel time, it's on the order of L over C, the length of the arm divided by the speed of light. And for the ground-based detectors, that's 3 or 4 kilometers divided by the speed of light, which is 3 times 10 to the 8th meters per second. And that is on the order of 10 to the minus 5 seconds. On the other hand, the period of the gravitational wave is on the order of 10 to the minus 2 seconds. So the test masses, which move in response to the gravitational wave, won't move very much during the time it takes light to travel through the interferometer arms. Now, this difference in timescales can be expressed as L over C is much less than the period of the gravitational wave, which is, of course, 1 over the frequency, which, to within a factor of 2 pi, is 1 over the angular frequency of the gravitational wave. So this tells us that omega times L is much, much less than C. Let's save this result for later. Now, the second assumption or approximation that I made in deriving this result for the phase shift was to adopt a Newtonian point of view and ignore the fact that the light in the interferometer is redshifted and blueshifted by the gravitational wave as space expands and contracts. So we ignored the redshift and blue shift of the light that's caused by the expansion and contraction of space. And we know that the expansion and contraction of space has this effect on light from our studies of cosmology. Recall that the expansion of the universe causes the cosmological redshift. This leads us to a common confusion about how interferometers work as gravitational wave detectors. It seems that if light expands and contracts along with space, then the phase of the light will be insensitive to the expansion and contraction. Therefore, light can't be used to detect gravitational waves. Let me try to summarize that argument. Light expands and contracts with space, so the phase of the light is indifferent to the expansion and contraction. Therefore, light can't be used to detect gravitational waves. Of course, this reasoning is wrong. What it fails to recognize is that the redshift or blueshift of the light is determined by the expansion or contraction of space during the time that the light is traveling in the interferometer, and that time is approximately constant. So that redshift or blueshift depends on the rate at which space is expanding or contracting. On the other hand, the phase difference, delta phi, depends on the actual amount of expansion or contraction. For example, consider a kind of step function gravitational wave that produces a permanent change in the arm lengths. Now send light through the interferometer. Because space is no longer expanding or contracting, the light is not redshifted or blueshifted. Its wavelength is unchanged as it passes through the interferometer. But because the arms have different lengths, there will be a phase difference between the X and Y light waves when they're recombined. Let's see how this works out mathematically. We've already estimated the phase difference, delta phi. We found that's equal to 2LA divided by C times omega for the light. That's the angular frequency of the light, times sine of omega times T naught. And this basically comes from the difference in light travel time times the angular frequency of the light. And of course, the difference in light travel time is just proportional to the difference in arm lengths. And that difference is equal to A times sine of omega t naught. So that's why these factors of A and sine omega t naught appear in our expression for delta phi. And by the way, a more careful analysis of the phase difference shows that this result is correct in the limit omega L is much, much smaller than C. Now let's estimate the change in wavelength of the light due to expansion or contraction of space. First, let's look at the light that propagates in the X arm. The fractional change in the wavelength, that's delta lambda over lambda, is equal to the fractional change in the arm length. So that's the change in the arm length during the light travel time divided by the length L. And that's approximately equal to the rate of change of the arm length times the light travel time divided by L. Now remember, the arm length is L plus L times A times sine of omega t in the z equals 0 plane. And the light travel time is 2L over C, and then we divide that by L. So of course these L's cancel, and then taking the derivative, what we're left with is 2LA divided by C times omega times the cosine of omega t, and we're assuming the light leaves the corner station at time t naught, so let's evaluate this at t naught. So this is our result for the change in wavelength for the light that travels down the X arm of the interferometer. So this is the X arm. And we have a similar result for the light that propagates in the Y arm, namely delta lambda over lambda equals minus 2LA over C times omega cosine of omega t naught. So let's compare these results with our phase difference, which is delta phi equals 2LA over C times omega for the light times sine of omega t naught. As you can see, the phase difference depends on the length difference between the two arms, which is proportional to sine omega t naught. On the other hand, the change in wavelength of the light depends on the rate of change of the arm length, which is proportional to cosine omega t naught. The other key difference in these results is that the change in phase depends on the angular frequency of the light, whereas the change in wavelength is proportional to the angular frequency of the gravitational wave. Now, the frequency of the gravitational waves from binary black hole and neutron star collisions, the events that the ground-based interferometers are designed to detect, is around a few hundred hertz. So this corresponds to an angular frequency of around 1,000 radians per second. On the other hand, the laser light used in the interferometers is in the infrared region, which is an angular frequency of around 10 to the 15 radians per second. So obviously the light frequency is much greater than the gravitational wave frequency, and the phase difference is a much larger physical effect than the red shifting or blue shifting of the light. So you can see from this analysis that although the expansion and contraction of space does affect the wavelength of the light in the interferometers, this effect does not cancel out the phase shift that's used to measure the gravitational waves. Now, admittedly, the calculations I presented in this lecture are not very rigorous, and it's always a good idea to follow up that type of rough analysis with a more rigorous derivation. So in the practice problem, you'll find a step-by-step description of a more careful calculation of these results for the phase difference and the fractional changes in wavelength. One of the things you'll discover if you work through the practice problems is that I've made a mistake in calculating delta lambda over lambda. The mistake came from right here. The arm length is actually L plus 1/2 L times A times sine of omega t. So this 2 should cancel this 2, which means I need to cross out this 2 and this 2.